The universe has a speed. Not the speed of light, not the speed of galaxies, but the speed at which space itself expands. For nearly a century, scientists have tried to measure this number with increasing precision. And today, we have two answers. One says 67, the other says 73. Both are measured in kilometers per second per megaparsec. Both are backed by world-class observatories. Both are independently verified, and both cannot be correct at the same time. This is not a rounding error. This is not a broken telescope. This is not a minor calibration issue. This is a fundamental disagreement about how fast the universe is expanding right now. The early universe, studied through the cosmic microwave background, predicts an expansion rate of roughly 67. But when we measure the modern universe using exploding stars and galactic distances, we consistently get about 73. That difference might sound small. It is not. In cosmology, a difference like this compounds over billions of years. It changes the age of the universe. It changes how structures form. It changes how dark energy behaves. It changes everything. If you think physics is settled science, this should make you uncomfortable, because the deeper we measure, the stronger this disagreement becomes. And the most disturbing part is this: both sides are right. The early universe measurements are extremely precise. The late universe measurements are extremely precise. Independent teams, independent methods, independent instruments, they all converge on the same split result. This growing disagreement has a name: the Hubble tension. And it is one of the most serious problems in modern cosmology. Not because we lack data, but because we have too much good data pointing in two incompatible directions. If the universe expanded at one rate in the past and a different rate today, something fundamental changed, and we do not yet know what. Tonight we are going to decode this tension step by step. We will explain how expansion is measured, why the numbers should match, and what could possibly resolve the conflict. Because if these two numbers truly refuse to agree, then our model of the universe may need more than a small correction. It may need an upgrade. To understand why 67 appears so confidently in cosmology, we must travel back nearly 13.8 billion years. The early universe left behind a faint glow, the cosmic microwave background radiation. This radiation is not random noise. It is a precise imprint of density fluctuations when the universe was only 380,000 years old. By analyzing its temperature variations across the sky, scientists can extract astonishingly detailed information about the geometry of space, the density of matter, and the initial conditions of cosmic expansion. Space telescopes such as Planck measured these fluctuations with extreme precision. From that map, cosmologists reconstruct a model of how the universe evolved. Within that framework, the expansion rate today is not measured directly, it is inferred. It is predicted from the physics of the early universe, and that prediction consistently lands near 67 kilometers per second per megaparsec. The mathematics are elegant. The model fits the early data beautifully. The cosmic microwave background agrees with the theory of inflation, with dark matter density, with baryon acoustic oscillations. It is one of the most successful scientific reconstructions in history. If you only look at the early universe, the case appears closed. The expansion rate should be 67. But this method assumes something important. It assumes that the laws governing expansion from the early universe until today have not changed. It assumes dark energy behaves consistently. It assumes there were no unknown influences between then and now. If any of those assumptions fail, the prediction could drift. And that is exactly where tension emerges. Because when we look at the modern universe directly, we do not get 67. We get something higher. The early universe is telling us one story, the present universe is telling us another, and physics demands that both stories connect through the same timeline. If they do not, then something happened between then and now that we do not understand.
That possibility is what makes this so powerful. The early universe gives us a prediction, the modern universe gives us a measurement, and they are not the same.
Unlike the early universe prediction, the modern measurement of expansion does not rely on ancient radiation. It relies on distance. Specifically, it relies on measuring how far away galaxies are and how fast they are receding from us. The key tool here is something called the cosmic distance ladder. First, astronomers measure nearby stars whose distances are known precisely. Then they calibrate a special type of pulsating star known as Cepheid variables. These stars brighten and dim at predictable rates. Their pulsation period reveals their intrinsic brightness. By comparing intrinsic brightness to observed brightness, distance can be calculated. Next, those Cepheids calibrate Type 1a supernovae, exploding stars that shine with nearly uniform luminosity. These supernovae can be seen across vast cosmic distances. Once calibrated, they act as standard candles. By measuring their redshift, the stretching of light due to expansion, scientists calculate how fast their host galaxies are moving away. This direct measurement of expansion repeatedly produces values near 73 kilometers per second per megaparsec. Not once, not twice, but across multiple independent surveys. Improved instruments, refined calibrations, alternative statistical approaches, they all reinforce the higher number. The error margins have shrunk over time, yet the discrepancy has grown more statistically significant. This is not a matter of careless measurement. It is a robust, repeatable result. So now we have two pillars of modern cosmology, one rooted in the early universe predicting 67 and one rooted in the local universe measuring 73. If one were clearly flawed, the problem would be simple, but neither collapses under scrutiny, and that is where the real tension lies. Because cosmology depends on consistency. The same universe must evolve from early conditions to present reality without breaking its own rules. If the present expansion is faster than predicted, then either the early model is incomplete or something altered the expansion history along the way. And that is where theoretical physics begins to tremble.
Before rewriting physics, scientists do what science demands. They search for errors. Could the telescopes be miscalibrated? Could dust distort brightness measurements? Could Cepheid variables behave slightly differently in distant galaxies? For years, teams have attacked the problem from every angle. New data from the Hubble Space Telescope refined distance measurements. Independent analyses cross-checked the supernova data. Alternative methods using gravitational lensing and time delays between quasar images produced expansion rates closer to 73. Meanwhile, baryon acoustic oscillations, ripples frozen into galaxy distributions, continued to support the early universe prediction near 67 when interpreted through the standard cosmological model. The tension refused to disappear. Each new dataset tightened the uncertainty bars. Instead of shrinking, the discrepancy hardened. Statistically, it has now crossed the threshold that physicists consider significant. The probability that this difference is random noise is extremely low. That forces an uncomfortable conclusion. If systematic errors are not the cause, then the model itself may be incomplete. But abandoning the standard model of cosmology is not a trivial step. The lambda CDM model, lambda cold dark matter, explains an enormous range of observations with remarkable success. It predicts large-scale structure, cosmic background patterns, galaxy clustering, and element abundances. To modify it, we must introduce new physics that solves the expansion mismatch without breaking everything else it gets right. That is a narrow corridor. And yet, researchers are now seriously exploring possibilities that would have seemed radical just a decade ago. Because when two precision measurements disagree at this level, the universe is not whispering, it is signaling. Either our understanding of dark energy is incomplete, or dark matter behaves differently than assumed, or there were additional particles in the early universe that subtly altered expansion, or gravity itself deviates from general relativity at cosmic scales. Each possibility carries profound consequences, and none of them can be dismissed casually. The tension is no longer a curiosity, it is a fork in the road. Either the discrepancy dissolves with better data, or it opens a door to new physics.